Hi, welcome to my channel, and in this video we are going to solve MIT Physics PhD qualification exam on quantum mechanics. So this question is asking us, so a particle of mass m is confined in a one-dimensional region between 0 and a as shown in this figure, and at time is equal to 0 we have given a wave function that look like this. So what we need to see, what we need to solve is what is the wave function at other time. So we need to find the evolution of this. And what is the average energy of the system at t is equal to 0 and at t is equal to t naught? And what is the probability that the particle is found in the left half of the box at t is equal to t naught? Okay, so from the problem you can see this is a particle in one-dimensional infinite well on an interval 0 to a. And this is the first problem you solve in quantum mechanics whenever you are introducing Schrodinger equation. And we know the stationary state of this system. You should remember this. It's given by the sin x, and the energy state is n square pi square this Planck constant square over 2m square for n is equal to 1 to 3. So we know this energy state. We given one at t is equal to 0. What is the state of the particle is in this infinite well? So common strategy in time dependent quantum problem is to write your station that at t is equal to 0 state as a linear combination of the energy eigenstate. And if you do that, so we can first plug in what is my first and the second eigenstate energy eigenstates are, and you can see these are my first and the second stationary states are. And now this is the math problem for you. You can expand this wave function and try to make this as a linear combination. You will get 2 over square root of 5, phi 1 plus 1 over square root of 5, phi 2 square, phi 2. So now you know the first two eigenstate appear. You could gotten some other eigenstate. I got these first two. So if there's some other question, they can put some other eigenstate, but the approach is gonna stay the same. And you know the coefficient now that is C1 2 over square root of 5 and 1 over square root of 5. So for the first question was, what is the wave function at a later time? T is equal to t naught. So each stationary state pick up a phase of e to the power minus I e n t divided by the Planck constant. So this comes from whenever you're trying to solve the Schrodinger equation, you separate the x component and the time component, and you want to see how the system evolves, you put this factor. And when you do that, you will get this answer, and this is the your state at t is equal to t naught. You just need to plug in t naught instead of t. I just left it as t, and this is actually very easy. So the next question is, what is the average energy of the system at t is equal to 0 and t is equal to t1? So we've seen the state at t is equal to 0 and t is equal to. So the first thing you need to notice is that Hamiltonian is time independent because your potential does not depend on time. So this Hamiltonian is time independent. And you know this phi is a superposition of energy eigenstate. And in both the cases, you know coefficient of the energy state, the square of this coefficient would give you the probability that your system is in that state. So your average energy becomes this formula. This is from the probability. If you've done some basic probability, you would know how to calculate the average of this. You should know what is the probability of that state happening. We know the state does not change in time. So if you calculate the state, if you take the state after at t naught or at t is equal to 0, you're going to get the same answer. You can get from here like this C1 square is 4 over 5. 4 over 5 would be the probability that your system is in this state 1. The particle is in this phi 1 state, and 1 over 5 with the probability your particle would be in stationary state 2. And now you can we know this E1 because we know what is the energy level. There's a infinite one-dimensional infinite well, and then you can plug all that in and you get this answer also. And t is equal to 0 and is equal to t naught would be the same. Okay, now let's do the last problem. What is the probability that the particle is found in the left half of the box? This is probably the easiest question, because if you don't know how to solve this, drop out of physics. Physics is not for you. I'm kidding. But if you don't know how to solve this problem, you need to go start learning quantum mechanics. So the basic idea in probability is you have a wave function, the square root, not the square root, the square of that wave function gives you the probability. So this is the formula. You need to be careful. This is your state at t is equal to naught. But you need to be careful when you're scaling out, because you have a complex number like this. E to the power I minus x is complex. So square root is a little different. So I can tell you how to do it. What you need to do is you need to take the complex conjugate of your wave function and multiply them. Don't use a plus b whole square. You're gonna get wrong thing. And there is an exercise for you. You need to simplify this. And one hint is you're gonna use the Euler identity, and you're gonna see how they simplified. And when then you can go I did not integrate it. This is also homework for you. You can integrate and you will get this answer. So I hope you like this video. If you do, give the thumbs up, and I will see you next time. And let me know what else you want to see. You want to see more such kind of qualifying exam, or you want to see something else. So I hope you like this video. If you do, give the thumbs up and subscribe, like, and share, and I will see you next time.